do.
20, 25
The solar tide, if you just use this solar tide number of 1/4 of a meter, we should be able to then alter that based on the new star, right? Which has 30 times the gravity, which makes it 30 times smaller. That brings it to 1 centimeter. But then it's bigger by a factor of, we decided,
10 to the 11. Because you have to, it goes as the radius to the 4th, which is 10 to the 8th, and then 1 over. Oh,
but the distance needs to be then.
The distance is 1/10.
The distance is actually bigger. Oh, no, the distance of the from the sun, that should be the same, right? So in which case, yeah, I mean,
Except
that would be a difference of 10 to the 7 meters then, right? No, we're saying it's a factor of 10 to the 11, but down by down by a factor, but it's only
So
by a
1
factor of 100.
centimeter, so
So
10 to the 9.
10 to the 9 meters, which is 10 to the 6 kilometers, which is 1,000,000 kilometers, which is bigger than these stars, which is actually half a million kilometers or something like that. So basically, it's big enough that you're in the regime where this simple approximations don't apply. These things are going to be probably fairly distorted, and they're going to be distorted in sort of egg shapes toward each other. But they're not so distorted that they should be touching, I don't think. I don't think this is a contact. I know that just looking at the light curve that they showed me at the conference. Okay, this is not a contact binary, so that's not going to be going on. But that's how you calculate it. If you want to know the height of the tide, it's 9.18 that you plug in. Whereas the height of the tides on this planet, for instance, you can calculate more easily. Say this is on the giant planet. Looking at the giant planet, the height of its tides relative to these 2 stars, it's going to be a factor of 2.2 bigger because the stars are bigger. It's going to be a factor of 2.8, 2.7. Where's my 2.7? I know I have it somewhere. Anyway.
2.7.
Oh, here we go. 2.7 cubed, because it goes as r to the minus 3.
That's 20.
Yep, this is where we did that. So a factor of 20 smaller, a factor of 2.2 bigger, so that's a factor of 10 smaller, plus then the fact that this radius of this planet is going to be 10 times Earth radius, so that's to the 4. So that's going to be 10 to the 4 times bigger than the tide on Earth. 10 to 3. Yes, you're right. I did one extra. Down by 10, up by 1,000. By 10,000. So it'll be 250 meters will be the size of the tide. That's pretty good. It's a pretty good one. Pretty good tide. Any moon of this planet, of course, would then have 2 different tides, right? It's going to have a tide from its parent planet and from its star. And those are going to be competing. The planet's going to win, though, because that 1 over r cubed, you just can't beat 1 over r cubed. That's really powerful. We also talked about Coriolis and centrifugal force in this one. I can't think of any way to relate those to this system, though. If you give me time, I'll come up with it. But you should be able to know those and be able to apply those as used in, a rotating coordinate system, as if you're standing on one of these stars that are rotating or something like that. Okay, chapter 10 then, we did do chapter 10, which was rotation. Yep. Oh, that was all about moment of inertia tensors. You guys know that. You guys know that cold, right? I should be able to tell you a system. You should be able to calculate its moment of inertia tensor. And then the last chapter we did is the chapter we did not did. The chapter that we are doing is on Hamiltonian. Looking at it this way, like that, I'll tell you right now, there's 4 problems. I said 1 problem on each chapter. There's 1 problem on chapter 8 about central forces. There's 1 problem on chapter 9 about non-inertial reference frames. There's 1 problem on chapter 10 about moment inertia tensors, and there's 1 chapter on 1 problem on chapter 13, which is the Hamiltonians. So study all that. It's all relevant. Furthermore, so we're talking about the rotational chapter. You're going to need to be able to generate a moment of inertia tensor. That's a given, okay? Everything in this chapter requires a moment of inertia tensor. Furthermore, You should be able to understand something about how that rotation is going to proceed over time. Whether it's like a top and it's going to precess, or whether it's not a top, it's just freely spinning in space. It's still not just going to spin there and stay unless what? Unless it's rotating around a principal axis. You should understand principal axes. You should know how to figure them out either quantitatively or qualitatively. If you if you get the right answers, I'm not gonna complain. So you should be either able to calculate them explicitly what the principal axes are of an object, or you should be able to intuit them. I'll tell you right now, the problem you have, you should be able to intuit them. You shouldn't have to explicitly calculate them. So I'm not going to expect you to do eigenvector, eigenvalue on the fly, unless you can't figure it out. I mean, I think it's a pretty simple system. And you should be pretty easy to figure out what the principal moments are, or I'm sorry, what the principal axes are. But if you can't, remember, you can always go back and calculate it. I won't object. Yeah?
I'm sure it's probably but can you remember the longest axis and the shortest axis of rotation have some property in the middle one?
Yes, right, the moments of inertia. So, right, yeah, there's going to be I1 and I2 and I3, which are the principal, these are the moments of inertia around each of the principal axes. The moment of inertia around the axis with greatest moment of inertia is stable. Motion around the lowest moment of inertia is also stable. It's rotation around the principal axis of middling moment of inertia, where we define them like this. Remember, we called them lambda, didn't we?
Yeah.
I remember that now. If you rotate around either of these, it's stable. If you rotate around this, it kind of goes haywire really fast. And we all decided that I was not telling you to experiment on your phone by throwing your phone, your $800 phone in the air. If you do this, please make sure you're over a couch. See, you're doing it already. So right around your phone, the greatest moment of inertia is this one, right? Okay. I have a good case. I feel comfortable with that. The lowest moment of inertia would be this one. That's pretty stable. But the least moment of inertia is that one. That's the one that immediately starts going haywire.
You mean that one's the middle?
This is the middling moment of inertia. Is that right? Yeah. This is the middling moment of inertia. This is the low moment of inertia, right? Everything's very close to the axis here. Everything's very far from the axis, spinning like this.
Did we ever establish a conceptual reason for that, or was it purely based on the math?
We did the math, and we showed that basically there's the
Experiment matched up.
and it matched the experiment, and we decided that was good. I don't even have a good sort of conceptual handle on why that is, but it's a cool result that if you follow the math through and do the experiment, it absolutely matches up. But I even can't give you a good conceptual reason why that happens. Yeah, this isn't even a dissipative system, right? I mean, as we'll learn in astrophysics, in any system with dissipation where there's some sort of friction, if you have a given amount of angular momentum, inevitably that dissipation is going to lower the energy of the system. But you can't get rid of the angular momentum. You will ultimately end up in a system where you're rotating around the principal axis with the highest moment of inertia. We'll talk about more of that in astrophysics. Any more questions about the exam then? More problems you need to do? There'll be one on each chapter. Make sure you know your precessions, your moment of inertia tensors. Make sure you can solve a Hamiltonian problem. You will have opportunities to do that in homeworks 14 and 15. So fret not. You will have many opportunities to do that between now and then. Going once? Going twice? All right. I actually, believe it or not, I already graded your homeworks from Monday, so let me hand those out. Homework 13s.
Are you actually going to be collecting homework 15?
No. I'd love to, but I just decided that it was more important for me to, or for you guys, to have that solution set. to know how to do. So I'm gonna hand out, there is a homework 15. You're supposed to do it, but it's really up to you, because I'm gonna hand it and its solution set out at the exact same time, to the extent that I really want you to be able to know how to do those problems. So I'm not gonna grade it, because you guys are gonna have the solution set. It seems kind of dumb. So you'll ultimately only be graded, therefore, on 14 homeworks. This is just saving me time tomorrow morning. All right, thanks for coming, guys. I really appreciate you guys coming. Both you guys that come to the afternoon sessions and those of you that are watching online. I appreciate you doing that. It really enables me to do my science and my scientific service responsibilities. I had sometime in some astronomers seem to travel more than all other physicists, and I don't understand why that is. Well, it's not vacation most of the time, although there was a week.
Correspond and collaborate.
The astronomers,
With
the
the
physicists
astronomers?
the physicists don't want to talk to each other? Is that what you're saying?
Maybe